Hello everyone, my name is Bharti Patel, Assistant Professor, Computer Science and Engineering Department, Chhattisgarh Swami Vivekanand Technical University, Bhilai. So let's begin with the detailed understanding of the today's lecture on advanced deep learning models for image classification and recognition. So image classification and recognition are fundamental tasks in the field of computer vision, enabling machines to understand and interpret visual information from the world around us. These tasks hold immense importance due to their wide range of applications and their potential to enhance various industries. So here is a brief overview of their significance. First one is automated understanding, second is medical diagnosis, third one is autonomous vehicle analysis, fourth one is agriculture, next is security and surveillance, then retail and e-commerce, then artificial intelligence assistance, then environmental monitoring and industrial quality control, next is accessibility, next one is entertainment and gaming, and the next last is social media and content filtering. In summary, image classification and recognition are foundational technologies that bridge the gap between visual data and machine understanding. Their applications span across diverse fields, impacting industries, services, and daily life, ultimately driving technological advancements and improving human experiences. So, image classification is a fundamental task in computer vision that involves assigning a label or category to an input image. The goal is to train a machine learning model to recognize and differentiate between the different objects or scenes or pattern within images. So, the model learns to extract meaningful features from the images and uses these features to make accurate predictions about the content of new or we can say unseen images. So, some of the applications for image classifications are like object recognition, medical imaging, security and surveillance, agriculture, autonomous vehicles, retail, natural resource management, and art and creativity. So, there are some traditional methods and their limitations. So, before the rise of deep learning, traditional methods for image classification often relied on handicrafted features and machine learning algorithms. So, some of these methods include like feature engineering and support vector machines, we can say SVM or bag of visual words, and another one is principal component analysis or we can say PCA. Then the next one is K nearest neighbor or we can say KNN. Then the histogram based methods, next is template matching, next most common method is naive Bayes classifier, and one of the method is decision trees and random forest. Then the next one is neural networks, that is before the deep learning. Then next one is scale invariant feature transform or we can say SIFT, color based methods and Gabor filters. So while these traditional methods contributed to the early advancements in image classification, they often faced limitations in handling complex and large scale datasets. So capturing high level features and adapting to variations, the emergence of deep learning models, particularly convolutional neural networks or we can say CNN, revolutionized image classification by automatically learning hierarchical features directly from raw pixel data and leading to the remarkable improvements in performance and robustness. So, some of the techniques, like one of the technique which is most commonly used like feed forward neural network. A feed forward neural network is the fundamental building block of deep learning models. It consists of an input layer, one or more hidden layers and one output layer. So, data flows through the network from the input layer to the output layer, and in between there are some hidden layers. So, with each neuron in a layer connected to neurons in subsequent layers. So, here is a basic Python code that is illustrating the concept of a feed forward neural network using the NumPy library. We can see in this code and you have to implement on your system and you can learn the output also. So in this we have to import the libraries, then we have to assign the values. For that we have to define the network architecture, which network we are going to take and how many layers with the values are defined here. So initialize the weights and biases. After that we have to give the input data. Then after that we have to forward the passes for all the hidden layers, and after that the output layer will generate the output. So print the output. So next one is backpropagation. What is backpropagation? Basically backpropagation is a key algorithm used to train neural networks. It is a process of adjusting the weights and biases in the network to minimize the differences between predicted outputs and actual targets which we are going to be implemented. So it works by calculating the gradient of the loss function with respect to the model's parameters and then updating the parameters in the opposite direction of the gradient. So here is a simplified Python code that is going to illustrate the backpropagation method in a simple way. This is a generalized code. We can apply this code and we can learn the output. So first of all we have to assume that we have some forward pass results with the target values. Then we have to use the backpropagation method with the detailed description of all the input layer, hidden layer and weight and bias. Then update the weights and biases. And for this we have to initialize the learning rate, which is very essential to know, because learning rate will define that the threshold value through which we can identify that our model is going to learn better or not. So according to that we have to define the weights and biases, and then we have to provide the values to that hidden layers. So please note that these code examples are simplified and intended for illustrating purposes. In practice, you would use deep learning frameworks like TensorFlow or PyTorch to efficiently build and train neural networks. So the concepts of feed forward and backpropagation are foundational to understanding how neural networks learn and make predictions. So some of the major points like which are very frequently used by using these deep learning methods. So role of activation function is most important and most commonly used. So we have to learn that what is activation function. In activation functions, it plays a critical role in neural networks by introducing nonlinearity to the model's computations. They enable neural networks to learn complex relationships and patterns within the data and making them capable of solving a wide range of tasks. Here is an overview of the role of activation functions in neural networks. So first one is introducing nonlinearity, second one is modeling complex relationships, third is feature transformation, fourth one is learning representations, fifth is gradient flow and backpropagation, sixth one is avoiding vanishing and exploding gradients, seventh one is squashing output range, and eighth one is sparsity and sparse representations. So commonly used activation functions that include some of the probabilities like hyperbolic tangent, or we can say 10H. So it is a similar to the sigmoid but maps input to the range, and the range is -1 to 1. And the next one is rectified linear unit, or we can say ReLU, which is most commonly used in our deep learning models. So in this outputs the input, it is positive or otherwise output 0, then helps to define that vanishing gradient problem and accelerate the training. So next is leaky ReLU. What is this? It is almost similar to ReLU only, but it allows a small gradient for negative inputs to address the dying ReLU problem. And the next one is parametric ReLU, or we can say p-ReLU. So it allows the negative slope to be learned during training. And the next one is exponential linear unit, or we can say ELU. which is similar to ReLU but with a smooth curve for negative inputs, which helps to prevent that dead neurons. Next one is Swiss, a newer activation function that combines elements of ReLU and sigmoid. So, selecting an appropriate activation function that depends on the specific task and network architecture and the potential challenges you might encounter during training. So, let's start with the CNN. So, going to start the introduction. What is CNN? So, CNN were inspired by the visual processing mechanism in the human brain. They consist of layers that automatically learn and extract features from images. Key components of a CNN include: first one is convolutional layers. These layers apply filters, or also known as kernels, to the input image. The filters slide over the image to detect specific patterns, edges, textures or other features. Convolutional layer are responsible for local feature extraction. Next layer is pooling layer, which is very important to know. After convolutional pooling layer, downsample the spatial dimension of feature maps. So, pooling reduces the computational load and extracts dominant features and introduces a degree of spatial invariance. Next is activation functions, which already we have discussed. So, nonlinear functions like ReLU are applied element wise to the convolutional outputs and introducing nonlinearity to the network. So, next one is fully connected layers. These layers process the high level features extracted by the convolutional and pooling layers. They make final predictions based on the learning features. So, this is all about the CNN introduction. Now, we are going to start the suitability for image data. So, CNN are uniquely suited for some of the image data type. So, some of the following reasons why it is suited for that CNN model. First one is local receptive fields. CNN mimic the way the human visual system processes information by focusing on local region of an image. So, this local connectivity is well suited for capturing spatial hierarchies and patterns. Next is translation invariance. CNNs are designed to be translationally invariant, meaning they can recognize pattern regardless of their position in the image. So, this is essential for identifying objects or features in different part of an image. Next one is hierarchical representation. CNN automatically learn hierarchical features starting from simple edges and textures in lower layer to complex object parts and high level features in deeper layers. Next is parameter sharing. CNN share weights across the image, reducing the number of parameters compared to fully connected networks. So, these enables CNN to efficiently handle large images. And the next one is reduced variance. Pooling layers downsample feature maps, reducing the spatial dimensions and making the network less sensitive to small translations and distortions in the input. So, next is feature visualization. In CNN, basically it can learn to generate meaningful visualizations of the learned features which aid in understanding what the network is recognizing. Then the most important one is transfer learning. In transfer learning, that defines the pre-trained CNN on large image data sets, example ImageNet, that can be fine-tuned for specific tasks with smaller data sets and leveraging the network's learning features. So, the availability of architecture, we are going to discuss some of the architectures about the deep learning model. So, various CNN architectures such as ELINet or we can say LINET, AlexNet, VGG, ResNet and Inception. These have been developed to tackle the different challenges in image classification, object detection segmentation, and many more. So in summary, CNN ability to automatically learn and extract features from images, their translation invariance and their hierarchical representation learning make them highly suitable and effective for a wide range of computer vision tasks involving image data. So next is feature hierarchy. Feature hierarchies play a crucial role in data representation and processing, especially in the context of machine learning and deep learning. They provide a structured and organized way of capturing complex patterns, or we can say features, and relationships within data. So here is why feature hierarchy are important, which is discussed with some of the important points, like first one is abstraction of information, second is effective representation, third is improved generalization, fourth is feature composition, fifth is invariance and robustness, sixth one is transfer learning, seventh one is interpretability and insight, eighth one is computational efficiency, and the ninth one is flexibility and adaptability. So in the context of deep learning architectures like convolutional neural network and recurrent neural network, which is called RNN, leverage feature hierarchies to extract and process data efficiently or effectively. So these hierarchies allow models to gradually learn increasingly complex and meaningful representations, making them capable of handling a wide range of tasks, from image recognition and natural language processing to game playing and autonomous driving. To demonstrate the importance of feature hierarchies using Python, let's create a simple example using a synthetic dataset and a basic neural network. We'll compare the performance of a shallow network with no feature hierarchy to a deeper network that can learn hierarchical features. So, we'll use the scikit-learn library for generating the dataset and Keras for building the neural network. So, this is the simple code. In this code, we have to see, first of all, we have to import the library, then we have to identify that which library function or which library package is important to build that model, and according to that we have to give the sequential layers. Then create a synthetic data set. We have some data samples with the 1000, that is the value, and the random state which is defined as 42. So, there are some values like xtrain, xtest, ytrain and ytest. According to that we have to define the size and we have to initialize the random state value. Then in the shallow neural network we have to define the model, or we can say the sequential model, which is the neural network based model. So in this model, the shallow model will define again the xtrain, ytrain and the epochs, or we can say the iterations, then the best size. So in this example, we create a synthetic data set with two moon shaped classes using scikit-learn's make moons function. We then build and train two neural networks, a shallow one with a single neuron and a deep one with two hidden layers of 10 neurons each. So by comparing the accuracy of the shallow and deep models, you should observe that the deep model with feature hierarchies performs significantly better. The deep network can learn to capture complex relationships within the data by gradually transforming and combining features through multiple layers. This demonstrates the importance of feature hierarchies in improving the capability of neural networks to handle intricate patterns and improve performance on various tasks. So basically overview of classic CNN architectures are here with some of the major types like LeNet, AlexNet, VGG and GoogleNet, which are very commonly used here in this real world problem. So an overview of each classical CNN architecture, which are already predefined here, along with a basic Python code example using the Keras library. which is here, with some note that these examples are simplified for demonstration purposes and may not match the original architecture in terms of complexity or accuracy. So, you have to justify it according to your necessity or the requirement. So, first one is LeNet. LeNet is one of the earliest CNN architecture designed by WAN, and we can say it is for handwritten digit recognition. It consists of convolutional and pooling layers followed by fully connected layers. This is the code. In this code, we can see that first of all we have to import all the libraries, major libraries function, then create a sequential model. That model will define the values and we have to analyze the result. Then add the first convolutional layer with 6 filters. Filters which will define the feature map, each with 5 cross 5 kernel. Then input shape that specifies the dimension of the input images. Here we are taking the input images with the pixel size is 28 cross 28 with the one channel for grayscale. Then add a max pooling layer with a pool size of 2 cross 2. This layer reduces the spatial dimension of the feature map by taking that the maximum value in each 2 cross 2 region. After that, we have to add the second convolutional layer with 16 filters and a 5 cross 5 kernel. Then next is add another max pooling layer to downsampling the feature map further. Then next, flatten the feature map to a 1D vector, because before connecting to fully connected layers, we need to do that feature map. Then add a fully connected layer with 120 neurons and ReLU activation function. Then add another fully connected layer with 84 neurons and ReLU activation function. The next layer is output layer. So, add the output layer with 10 neurons, that is corresponding to the number of classes, or we can say the category. So, we are using here the softmax activation function. Then in the last, print a summary of that model architecture. So, next is AlexNet. AlexNet developed by Alex, which is basically defining the breakthrough in image classification. It features multiple convolutional and fully connected layers and popularized the use of ReLU activation function and dropout regularization. So, by the Python code we can learn. In this code we can see that here some library, in this code we can see there are some library functions. We have to import all the library functions, then create a sequential model for AlexNet, then add the first convolutional layer with 96 filter and a large 11 cross 11 kernel and ReLU activation function. Then the strides parameter indicates a stride of 4 in both dimension, that means for downsampling. Then input shape specifies the dimension of the input images, that is 224 cross 224 pixels with 3 channel of color. Then next is add a max pooling layer with a pool size of 3 cross 3 and a stride of 2 cross 2. This layer reduces the spatial dimension of the feature map and introduces transition variance. So, after that add the second convolutional layer with 256 filters and a 5 cross 5 kernel. Then add another max pooling layer to downsampling the feature map. After that we have to add the 3 more convolutional layer with 384, 384 and 256 filters and 3 cross 3 kernels. After that add another max pooling layer for the analysis. Then flatten the feature map to 1D vector before connecting to fully connected layer. Then add 2 fully connected layer with 4096 neurons and ReLU activation function. After that add dropout layer with a dropout rate of 0.5 to reduce the overfitting. Then add the output layer with 1000 neurons and then print a summary of the model architecture. So, this is one of the important model. Then the next one is VGG16, that is called Visual Geometry Group. VGG16 and VGG19 are popular CNN architectures that is categorized by their deep and uniform architecture. They use small 3 cross 3 filters throughout the network and are known for their simplicity and effectiveness. So this is the code again for VGG16. You have to implement on your system and you can get the output. This is the generalized code. In this code we have to import the library, then again create the sequential model for VGG16, then add the first convolutional layer with some filters and the kernel value. Then ReLU activation function is used here for element wise output generation. Then input shape specifies the dimension of the input images. After that, add the another convolutional layer with specified filter value and the kernel value. Then add a max pooling layer with pool size of 2 cross 2. These layers reduces the spatial dimension of the feature map. Then add the 2 more convolutional layer with 128 filters and 3 cross 3 kernels. Then add the another max pooling layer. Then after that, we have to add 3 more convolutional layer for the output generation. Then max pooling layer is added in the pattern of 512 filters and 3 cross 3 kernels. After that, we have to add another max pooling layer according to the requirement. Then we have to add the convolutional layer with some more filters and kernels. Then again adding more and more max pooling layer, we have to flatten the feature map to a 1D vector before connecting to fully connected layer. Then fully connected layer is added with the 4096 neuron and ReLU activation function. At the end, we have to add the output layer with 1000 neurons and then print a summary of the model architecture. The next most important model is GoogleNet. GoogleNet, also known as a Inception V1, that introducing the concept of inception modules that perform multiple convolution of different filter sizes in parallel, allowing the network to capture a wide range of features. So next is introducing to ResNet and the concept of residual block using Python, which is very important to know. ResNets are a type of deep neural network architecture that introduces the idea of residual learning, which helps address the vanishing gradient problem and enables the training of very deep networks. So here is an example of a simple residual block implementing using Python and Keras. You have to implement this code and you can get the output. In this example, residual block function defines a basic residual block with 2 convolutional layers. The shortcut connection is added to the output to the second convolutional layer, and the function takes an input tensor, the number of filter for the convolutional layers and other optional parameters. The model is then built using Keras with the residual block applied to the input tensor. So next important topic is transfer learning. Basically, in this approach, a pre-trained model which has acquired meaningful feature representations from a large and diverse dataset serves as a fundamental starting point for a new problem. By fine-tuning and adapting the pre-trained model using a smaller task that specifies the dataset, transfer learning enables the model to leverage its existing knowledge to better grasp the new task. In this example, we import pre-trained model like VGG16, ResNet 50, Inception V3, MobileNet, Exception and DenseNet 121 from the Keras library. So specifying that we want to use the weights pre-trained on the ImageNet dataset, we then print summaries of these models to get an overview of their architectures. Keep in mind that each pre-trained model has its own specific input size and pre-processing requirements. So transfer learning architectures are like ResNet, VGG, Inception and some of the MobileNet other models which are very useful, and we can see this by the Python code like using TensorFlow and Keras library. This is the code for transfer learning models. You can repeat the same process for VGG, Inception and MobileNet models. Make sure to adjust the image preprocessing and input shape according to the specific requirement of each model. So conclusion and outcomes. In conclusion, advanced deep learning models have significantly transformed the landscape of image classification and recognition. These models, including convolutional neural networks, residual networks, inception networks and others, have yielded remarkable outcomes in terms of accuracy and performance. by automatically learning intrinsic feature and hierarchies from raw pixel data. These models have demonstrated unpredictable capabilities in accurately identifying and classifying the object within the images. As the field continues to evolve, advanced deep learning models are poised to drive further advancement in image understanding, shaping the future of computer vision and paving the way for innovative solutions across industries. So, thank you. Looking forward to our next engagement, be it in an upcoming video or whenever. Thank you. Looking forward to our next engagement, be it in an upcoming video or whenever your requirements necessitate. Evoke a sense of anticipation and enthusiasm. Until then, take care and goodbye.